Hello, this will be a demonstration of proposition 6 from book 6 of Euclid's Elements, which says that if two triangles have one angle equal to one angle, and the sides about the equal angles proportional, the triangles will be equiangular and have their corresponding sides proportional. This is a partial converse of proposition 6.4. And again, this is going to be another similarity theorem. So what we're given is the triangle ABC. Let's say it looks something like that. A, B, C. And likewise, we're going to have the triangle D, E, F, like so. D, E, F. Such that one angle is equal to one angle. In this case, the angle ABC is equal to the angle EDF. And that the sides about this equal angle are going to be proportional. That is to say that BA is going to be to AC just as ED is to DF. So what we're going to prove with this is that the angle ABC is equal to the angle DEF, and that the angle BCA is equal to the angle EFD, and also that AB is to BC just as DE is to EF, and finally that BC is to CA just as EF is to FD. We're going to begin in similar manner to the previous proposition 6.5. So on the straight line DF, and at the points D and F respectively, we're going to make the angles FDG and DFG equal to angle BAC or EDF respectively, and equal to angle ACB. So we're going to have this first angle FDG equal to the angle BAC. That is going to look something like that. And of course, this angle FDG is equal to BAC, which means, of course, it's also going to be equal to an EDF. And we're also going to construct the angle DFG at the point F such that it is equal to ACB. So, like that. Okay. And we can do this, of course, by a proposition 123 on a given straight line and at a given point on it to construct a rectilineal angle equal to a given rectilineal angle. Okay, so knowing that the angle BAC is equal to the angle FDG, and that a second angle BCA is equal to a second angle DFG, we can say by virtue of proposition 132 and some other little thinking like common notion 3, that the third angle ABC is equal to the third angle DGF. Right, this is again something I explained at the end of my 6.4 video, that if two triangles have two angles equal to two angles, then the third angle should be equal to the third angle. So this is the third time we've seen this actually. Okay. Now, knowing that the triangle ABC is equiangular with the triangle DFG, we know that the sides about the equal angles are proportional, that is by proposition 6.4. So we can say that the side BA is to the side AC, just as the side GD is to the side DF. So you notice that the angle at A is equal, or the angle BAC is equal to the angle FDG, which means that the straight lines containing these angles are also going to be equal. That is to say that that BA is to AC, which contains the angle BAC, is to FD to DG, which contains the angle FDG. Again, that's by 6.4. So BA is to AC just as GD is to DF. But we were given that BA is to AC just as ED is to DF, which means we have two ratios which are equal to the same ratio, which means that by proposition 5.11, the two ratios shall be equal to one another. So we can say that ED is to DF just as GD is to DF. And when magnitudes have the same ratio to the same, they are equal. That is proposition 5.9. So we can say that ED right here is equal to a DG right there. Now, ED being equal to a DG, we have just shown that, and DF being common to both the triangles DEF and DGF, and finally, that the angle EDF is equal to the angle GDF because we made it that way in the first step, we have two triangles which have two sides equal to two sides, and the angle contained by the equal sides equal as well, which means that these triangles are equal in all respects, namely that the angle DFE be equal to the angle DFG, and that the angle DGF be equal to the angle DEF. Now, this triangle ABC is equiangular with the triangle DGF, but it's just now been shown that the triangle DEF is also equiangular with the triangle DGF, which means by combination 1, these two triangles, ABC and DEF, are equiangular to each other themselves. And being equiangular, by proposition 6.4, we can say that their corresponding sides are proportional, so that in the end we can say that AB is to BC just as DE is to EF, and finally that BC is to CA just as EF is to FD. Now this is all that we set out to prove. We set out to prove that the angle ABC is equal to the angle DEF, that the angle BCA is equal to the angle EFD, and that AB is to BC just as DE is to EF, and finally that BC is to CA just as EF is to FD. We have just done that. We've shown that the triangles ABC and DEF are equiangular, and being equiangular, the sides about the equal angles must be proportional. Therefore, we are done with the proposition, therefore, etc. QED. This is another similarity here within book 6. So 6.4 is angle-angle similarity, that if two triangles have two angles equal to two angles, then they will have the sides about the equal angles proportional. And the previous proposition 6.5 was the side-side-side similarity theorem, that if triangles have their sides proportional, then the angles contained by the proportional sides are equal. And in 6.6, we have the side-angle-side congruency theorem. So we have one angle equal to one angle, in this case the angle BAC equal to the angle EDF, and the sides about the equal angle proportional as well, that BA is to AC just as ED is to DF, which means we have one angle equal to one angle and two sides which are proportional to two sides. So this is going to be our side-angle-side similarity theorem. Not, of course, to be confused with proposition 1.4 side-angle-side congruency. This is just similarity, although I suppose congruency is a special case of similarity. Regardless, that's the end of this proposition, and that's the end of all that I have to say about it. So I'll end the video here and move on to 6.7.